Alright, let's get started. So, in this video, I'll be talking about molecular geometry, Lewis dot structures, bonds, resonance, sigma bonds, hybridization, all that good stuff related to Lewis structures and eventually our molecular geometry. And before we talk about molecular geometry and any of the things, actually, we need to cover a very important thing about electronegativity. So here I have a periodic table which I labeled for you actually. So if we take a look at this part right here in green, it says the chemistry 1 definition of electronegativity is the strength in which an atom pulls electrons to itself. So it's an atom's strength in pulling electrons to itself. All right, this big blue arrow across the periodic table shows us the trend. And if you wanted to see the detailed trends, we have it here in red. The electronegativity increases as you go up and right. And in the blue here, we have, it says trend stops at fluorine because noble gases are not electronegative. The reason why noble gases aren't electronegative is because they have a full octet, meaning that they have 8 valence electrons in their outermost shell, and therefore they do not want any more electrons because they're all happy and satisfied. So valence are in this group here, the noble gas group. All of these have a valence electron count of 8, and they are all happy. So the trend stops at fluorine. So fluorine is the most electronegative element. All right, we can reference back to the periodic table, but it's there if you need it. And also in the description below, I created this worksheet myself. So this is available if you want more practice. If you want to look back at it, I have the key and the worksheet and this table as well. So if you need more practice, go check out that link in the description. And let us get started with number 1. And the direction reads, for each of the following molecules slash compounds slash polyatomic ions, draw the Lewis dot structure and answer all applicable questions. And we're starting off with carbon dioxide, CO2. And in order to do this, we have to take a look at the molecular formula first, which is given. The formula CO2, we have carbon and oxygen. We have 2 oxygens, actually. So if we look at our periodic table, let's find carbon and oxygen. Carbon and oxygen. So carbon has a valence electron count of 4, and oxygen has a valence electron count of 6. And the way we know this is because we just count the groups. 1 valence, 2 valence, 3 valence, 4 valence, 5 valence, 6 valence, 7 valences, and 8 valences. And so this group, all of the elements in this group here has 4 valence electrons. So carbon has 4. That's 4 valence electrons. And if you don't know, that E minus symbol means electrons. Electrons. And VE is valence electrons. Something to note. Alright, so carbon has 4 valences, and we have oxygen, we have 6 valences times 2, which is 12 valence electrons. Alright, so if we take a look here, the total amount of valence electrons is 4 plus 12, which is 16. 16. And in order to determine the central atom, when you determine central atom, it will always be the element, or let's say atom with lowest electronegativity. This right here means electronegativity. It's a big word. That means electronegativity. Right there. Alright, put that in quotes for you. Alright, and with that information, in order to determine the central atom, we have to look at our periodic table again. So, in elements carbon and oxygen, let us determine which one has the lowest electronegativity. Alright, you probably know this by now. Increases left to right. And so oxygen will have more electronegative forces than carbon. And because we want the most negative, or sorry, least electronegative element in the central atom, we're going to say carbon is our central atom. Okay, let's take a look at the charge of the molecule. It says, if applicable. In order to determine the charge, we look at this. If there's no number on top there has no charge. There is no charge on this element. Let us draw the Lewis dot structure. So knowing that we have 16 total valence electrons, if we draw the Lewis dot structure, we're going to base carbon in the middle, and we're going to have oxygen branching out from carbon. We have 1 carbon and 2 oxygens, as stated in the molecular formula right there. And I always start with one single bond. That is a single bond right there. This is also a single bond. I always start with a single bond here and here to signify and connect all of these elements or atoms together. Each bond listed here accounts for 2 electrons because this is a covalent compound. In covalent compounds, electrons are shared in pairs. So this is 2 electrons and 4 electrons. Our total, we have to get to 16. So let's count backwards. 16 minus 2 minus 4. Minus 4 is 12. 12 valence electrons. Now what I'd like to do is I like to make every element happy. So I'm going to assign electrons to oxygen. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And now we have all of our electrons that we need on our Lewis dot structure. But after we do that, we have to double check and make sure that all elements have an octet and they're full happy. If we look at oxygen here, we have 2, 4, 6, and this is 8. Remember, this counts for 2. And so oxygen on the left-hand side is happy. Same deal here, 2, 4, 6, 8. This one's happy. But the issue here is that carbon is not happy because it needs 4 bonds, or lone pairs, or electrons, but it only has 2. Well, each one is 2, so it technically has 4. And so in order to fix this issue, we need to remove one set of lone pairs. So these 2 electrons is called lone pairs. And if you look at the name, it's called a pair because it's a set of 2 electrons. And so that's a lone pair. Keep that in mind. We need to remove one set of lone pair on each side that was here. We need to make it a double bond. 1, 2. There we go. And now if you take a look at carbon dioxide again, we're going to have 1 lone pair, 2 lone pairs, and 2 bonds. And this has become a double bond now. And instead of being a double bond, now every element's happy. 2, 4, 6, 8 on oxygen. 2, 4, 6, 8 on carbon. 2, 4, 6, 8 on this oxygen. And therefore, we know that this structure is the correct Lewis dot structure. And with that information, we can answer the questions on the bottom. The number of single bonds, we have 0. So it looks like a 6. 0, because these are all double bonds. If we look at our bonds in our CO2 molecule, we have 2 double bonds. And same deal, no triple bonds. Alright, let's take a look at molecular geometry. The molecular geometry, you only see like 2, 3, 4, 5, 6 types of molecular geometry. And it's important that you memorize all of them, which I'll help cover in this video. My worksheet will cover all of the 6 geometries that you do need to memorize. So carbon dioxide here, we can see that it has a linear molecular geometry. And this is because there are no lone pairs on the central atom, and these are all going to be in a straight bonded atom. And that's because it's based on the VSEPR theory. It's spelled VSEPR, and it's VSEPR theory. And this stands for valence shell electron pair repulsion theory, which means that electrons will arrange itself in a way that it has the least repulsion against each other. And because we have one end of the oxygen here and another here, and the carbon in the middle, it's going to arrange itself like this. And so these are at 180-degree angles, and it's the farthest away it can be with still sharing electrons with our C in the middle. And with that information, we do know that the bond angle is 180. That's 180 degrees. And we can move on to this section right here where it asks us about bonds. If we look at sigma bonds, if you remember, the only two types of things that we need to count for hybridization is going to be sigma bonds and lone pairs. Number of pi bonds we do not count for hybridization. If you look at sigma bonds, we only count one of the bonds, and it has to be on the central atom. So our central atom is carbon, and we have a double bond here and a double bond here. And so with this double bond, only one of these here, one can count for a sigma bond. This is the symbol for sigma. That's sigma. And the other one here, it's a pi bond. That's that pi. That's the mathematical pi. You can write it either way, but that is the pi bond. So if we have this information, we can solve the question that it asks us. The number of sigma bonds is going to be 1 here, 2 there, because it's on the central atom. The number of lone pairs on the central atom, we have none, 0. The number of pi bonds on the central atom, we have 1 here and 2 there. And so the hybridization, a lot of people get confused with hybridization, but you have to use the finger rule. So the number of sigma bonds plus lone pairs is how many fingers you're going to hold up. So in this case, you're going to hold 2 plus 0 fingers up, which is 2 fingers. So go ahead and hold up your fingers now with 2. You have 2 fingers up, and fold one of them down to go account for the S. And the remaining amount of fingers that you're holding up will be attributed to the exponent of the P. So your hybridization options are either going to be SP, SP2, or SP3. So we always have SP, and so you're good to just write SP. And remember, you hold up 2 fingers, but you fold 1 finger down for S, and the remaining number goes right there as the exponent. So in this case, we have 2 plus 0, which is 2. So 1 folds, and we have 1 finger holding up left. So our exponent for that is SP1, which is the same thing as SP, hybridized. All right, last question. Is it resonant? And it says, if yes, draw the applicable structures below. And resonance is defined by the fact that if your Lewis dot structure has a double bond or a triple bond that can be shared between 2 different spots. So in this case, we have 2 double bonds. So even if we switch the locations of these, it's going to be identical. So it doesn't have a resonant structure. So no, it is not resonant. And we'll see more example of this in future questions on the next page as well. Taking a look at the second example, we have BH3. Let us count the valence electrons for this. Boron, 1 boron. Let's see here, 1 boron and 3 hydrogens. So if we look here, our boron, let's erase the carbon. Boron and 3 carbons. So our boron's here, or sorry, hydrogens, 3 hydrogens. So if we have boron here and it's on the 3 group, we're going to have 3 valences for boron and 1 valence each times 3 for hydrogen. So we're going to have a total of 6 valences. 6 valences in BH3 because our boron here has 3 valence electrons and hydrogen has 1 valence electron times 3. and the sum of 3 plus 3 is 6. The central atom is going to be boron. Boron, because hydrogen can never be the central atom. Hydrogen, let's make a note here. Hydrogen can never be central atom. Alright, that's just something you have to memorize. Hydrogen only needs one bond to satisfy its octet, so it can never be the central atom. The charge of the molecule on BH3 is 0. There's nothing right there. And we can just put, let's put Na, not applicable. Let's write that a little better. And let's draw the Lewis structure. We know that the central atom is boron, and we're going to have 3 hydrogens branching off of it. One key thing to note here is that boron is special because the term to remember this is boron the moron. And if we look here, we have 1 word, 2 words, 3 words. So 3 words. It only needs 3 bonds for full octet. Full outer shell, we'll call it. And there's a lot of elements that do not abide the octet rule of 8 valence electrons in the outermost shell to be happy, and boron is one of the major ones. Boron only needs 2, 4, 6 valence electrons for satisfied. And with that correct Lewis dot structure, you can go ahead and start the questions. And if you since it's chemistry 1, if you draw your boron like this, I don't think the teacher will count you wrong. The more correct way is to draw it like this. If we look here, the number of single bonds, we have 1 single, 2 single, and 3 single bonds here. We have no double bonds and no triple bonds on the central atom. The molecular geometry for BH3, if you think about it, is going to be trigonal planar. That's trigonal planar. It's not triangular, it's trigonal. Remember that. And the bond angle is 120 degrees because it's a circle and you divide it into 3 pieces and each element sits right there, equidistant from each other and the farthest away possible, 120 degrees. The number of sigma bonds on the central atom, we count 1, 2, 3 sigma bonds. Lone pairs on the central atom, we have none, and therefore we have no pi bonds as well because it's only single bonds. And so the hybridization, you're going to hold up 3 fingers, 3 plus 0, and you're going to bring one down for the S, and the remaining fingers go on the exponent for the P, which is 2. So BH3 is sp2 hybridized. Looking at resonance, we have no double bonds or triple bonds, so it is not resonant. And that's it. Moving on to SO2. SO2 is a little special because in chemistry 1, you do not learn something called formal charge, which tells you the correct way to draw Lewis dot structures. So in this case, I'm going to make up one of the wrong answers for SO2, but in real life scenarios, you would calculate the formal charge and decide upon the correct SO2 Lewis dot structure. But since you're Chem 1 students, you do not need to know anything about that. So however you draw SO2, just make sure you can show resonance, which we'll talk about later. Looking at SO2, we have S and O. We have 2 of the oxygens. So we have sulfur here and oxygen here. And we have 2 of these. So they're all in group 6. So there's 6 valence electrons here. And 6 times 2 is 12 valence electrons here. And so we have a total of 18 valence electrons for SO2. So 18 valence electrons because this is 6 valence electrons and this is also 6 times 2 valence electrons and the sum is 18. Central atom is going to be sulfur because if we look at our periodic table, we know that sulfur is less electronegative than oxygen because the periodic trend increases as you go up and sulfur is below oxygen. So it is least electronegative compared to oxygen. There's no charge on the molecule because it doesn't have that charge listed right there in that space. So it has no charge. The Lewis dot structure for SO2, we're going to start with S, give each connection with oxygen a bond here, and we're going to count to 18 valence electrons. 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, and if our octets are full on all of our exterior bonded atoms, excluding the central atom, so we have oxygen with a full octet 2, 4, 6, 8, and 2, 4, 6, 8, we're going to go ahead and shove all that remaining electron on sulfur. So 2, 4, or sorry, 1, 2, which completes our 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. And we have to look at now our individual atoms and compare if they have the correct octet. Oxygen is happy with 8 on both sides, but sulfur only has 3. And so in order to remedy this, we need to cut off one of these here, which I'll do right now with my eraser tool, if I can correctly scratch that off. And we're going to create a double bond here. So this sharing of that valence electron or lone pair that was here is going to move here and make sulfur happy. Oxygen also is happy because it still has 2, 4, 6, 8 and 2, 4, 6, 8 on both sides, and now sulfur has 2, 4, 6, and 8. So this is a very happy sulfur dioxide molecule and Lewis dot structure. And so if we take a look at this, and if we look at single bonds, we have one single bond here, one double bond here, and no triple bonds. The molecular geometry for this element here is bent. It's bent because we have a lone pair here that exerts a force downwards against the oxygens here. So the oxygen is going to move down this way, and it's going to create a bent structure because electrons repel. All right, and so based on your chemistry 1 knowledge, you should know that if the bent structure has one lone pair on the central atom, it's going to be an angle less than 120. So angle less than 120 degrees. All right, and number of sigma bonds, we're going to count 1 and 2. Lone pairs, we're going to count 1. And number of pi bonds, we're going to count that bottom one on the double bond right there, 1. Hybridization, we're always adding what to? The sigma and the lone. 2 plus 1 is 3. You hold 3 fingers up, fold 1 finger for the S, and the remaining fingers go on the exponent for P. And that right there number is going to be 2 because you only have 2 fingers left after accounting for the S. So your hybridization is sp2. Looking at resonance, we do have resonance here because this double bond can move over here, this single bond can move over here, but it would still be SO2. So in order to show that, we're going to draw it like this. We're going to draw the one we drew up on top. And we're going to show it with double arrows. This right there shows resonance. And you don't need to put this part, but just show that double arrow right there. This is the most important part of resonance. And now we're showing this, but with the double bond on here and the single bond on here. But it's the same structure. So we're going to do SO 1, 2, 3, 4, 5, 6, and a double bond O 2, 3, 4. And that is going to be our resonance structures. Very simple. And to answer this question, yes, it is resonant. All right, moving on to our 4th question, CH4. Ooh, it's a tough zoom. All right, carbon on the periodic table is going to have 4 valence electrons. H4, 1 times 4 valence electrons, for a total of 8 valence electrons. And if you still don't know how to calculate valence electrons, I recommend you go to your teacher ASAP and ask them to teach you valence electron counting. But I am the best teacher out there, so I will teach you how to do that again. Carbon's here in group 4, it has 4 valence electrons. Hydrogen is in group 1, so it has 1 valence electron. And since our compound is CH4, we're going to have 4 valence here and 1 times 4 valence here, for a total of 8 valence electrons. Alright, the central atom is carbon, because it's the least electronegative, and hydrogen cannot be a central atom. And the charge of the molecule is 0, not applicable, because it doesn't have that number on the corner right here. Lewis dot structure, we're going to put C here, and each hydrogen is going to get a nice single bond, and that's going to be it. 2, 4, 6, 8 out of 8 valence electrons, and you are very happy. The single bonds, we have 4. No double bonds and no triple bonds. The molecular geometry for this shape, with 4 bonded atoms and no lone pairs, is tetrahedral. Once again, this part's memory. Bond angles 109.5 degrees. Looking at sigma bonds, we're going to have 1, 2, 3, 4 sigma bonds, no lone pairs on carbon, and no pi bonds, because they're all single bonds. Once again, you hold 4 fingers up, 1 goes to S, fold 1 finger down, the rest go as exponents to the P. sp3 is your hybridization. We have no resonance here because there's no double or triple bonds, so no, it is not resonant. Okay, next one, NH3. NH3. Nitrogen will have 5 valence electrons. Hydrogen will have 1 times 3 valence electrons, for a total of 8 valences. Nitrogen is your central atom, because hydrogen cannot be a central atom. There is no charge on NH3. Once again, put N and connect all your H's, and note that we need to make 8 valence electrons. 2, 4, 6. But hydrogen can only receive 1 bond, as we talked about earlier, so the remaining has to go on lone pairs on the central atom. Remember, if we have a full octet or full satisfied valence electron outer shell, we shove everything else left over on the central atom. This gives us our completed Lewis dot structure. We have 3 single bonds, 1, 2, 3. No double bonds and no triple bonds. The molecular geometry for NH3 with 1 lone pair is trigonal pyramidal. Trigonal pyramidal. Alright, and for trigonal pyramidal, the angle is 107 degrees. Once again, that blue part's all memory. The number of sigma bonds, we're going to have 1, 2, 3, because they're all single bonds. 1 lone pair on the central atom nitrogen, and no pi bonds because they're all single bonds. Add 3 plus 1 because it's sigma plus lone, and we're going to have 4 fingers. Put 1 finger down for the s orbital or s hybridization, and put the remaining number on your exponent for p. sp3 is your hybridization. I'm moving on to, is it resonant? It has only single bonds, so no, it is not resonant. Moving on to H2O, that's water. Total valence electrons, once again, 6 valence electrons plus 1 times 2 valence electrons. That's 8 valence electrons. Central atom is oxygen, because hydrogen cannot be the central atom. And there is no charge on the central atom, or molecule. Okay, put oxygen in the middle, and draw water, the H's, like that. connect your H's, and because H's are happy with one bond, we have to put the remaining 4 electrons on the central atom, and that will be water. But if you can memorize it in a different shape for Lewis dot structure, it'll save your life on the test. The way I recommend you write water is bent. So you draw the oxygen and hydrogen like this, and give your oxygen 4 valences like this. That is the preferred way of drawing water, and you can very clearly see that it's literally bent. So it'll literally give you molecular geometry for free. So let's put or, but this shape is preferred. Number of single bonds, 1, 2. Double bonds, we have none. We have no triple bonds as well. Molecular geometry, as I've said, is bent, and because it has two lone pairs instead of 1, it's going to have a bond angle that is less than 120. If you want to be exact, it's 105 degrees. Number of sigma bonds on water, we're going to have 1, 2. They're all single bonds. 2 lone pairs on our central atom oxygen, and no pi bonds. Hold 2 plus 2 fingers up, which is 4. Bring 1 down for the S, and rest go on P. So sp3 hybridized. And looking at resonance, it only has single bonds, so it is not resonant. Alright, let's take a look at our last question. This is CO3 2-, that is the carbonate ion, carbonate polyatomic ion, and it has a charge of 2-. So carbon has 4 valence electrons. Oxygen times 3 has 6 times 3, 18 valence electrons. And this 2- tells us that we have to add 2 valences. Now, if it was something like NH4+, where it has a plus as the charge, this means to subtract 1 valence electron. And since it's negative 2, 2-, we're going to add 2 valences. 4 plus 2 is 6, plus 18 is 24 valence electrons. The central atom is going to be carbon, C. Because once again, if we take a look at our periodic table, we are choosing the least electronegative, and we have carbon versus oxygen, and we know that electronegativity increases left to right, and carbon is less than oxygen, so it will be the least electronegative in the compound or polyatomic ion, therefore is the central atom. The charge of the molecule is 2- because it literally says right there. And because we have a charge, we're going to have to add brackets to the Lewis dot structure, which I'll show you how to do. Once again, put carbon in the middle. Make your bonds to oxygen. And that's 2, 4, 6. And we're aiming to go to 24. Alright, so we're going to fill all our oxygens, make them happy. 5, 6, 1, 2, 3, 4, 5, 6, 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26. So we have an issue here. All of our oxygens are happy, but one issue is that carbon is not happy with 4, and we have more electrons than what we had here. So in order to fix this, what we're going to have to do is create some double bonds. So instead of having a oxygen with 3 sets of lone pairs, which is 6 valence electrons, we're going to have one double bonded and rather have 2 sets of lone pairs. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, which matches our valence electron count. And oxygen is happy with 8, here 2, and here 3. And this time carbon has 1, 2, 3, 4 bonds, which is 8 valence electrons, and this is our complete Lewis dot structure. And because it has a charge, we do need to put brackets around this and put the charge in the top right corner of 2 minus. That charge comes from this right there. Number of single bonds, we have 2, 1 double bond, and no triple bonds. The molecular geometry for CO3, 2 minus, if we take a look, we have 1, 2, 3 bonded atoms with no lone pairs that was supposed to be here. So this will be trigonal planar. Trigonal planar with an angle of 120 degrees. Alright, once again, blue parts memorization, so you should probably memorize it. And we're counting sigma bonds. We have 1, 2, 3 sigma bonds. No lone pairs on the central atom carbon. And this bond right there that we didn't count on the double bond is a pi bond. So when we do hybridization, we always count sigma plus lone. So 3 plus 0 is 3. You hold up 3 fingers, fold one down for the S, and then the rest go on the exponent for P. sp2 is your hybridization. And in this case, it is resonant because it has a double bond that can go either here or here, and it'll still be the same structure. So in order to draw this, you do need to draw all of the structures. So it's going to we're going to have 3 structures. So if you do carbon, oxygen, 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 this time we're going to have double bond here. 1, 2, 3, 4, 5, 6. And we do need to do the brackets as well. Let's draw that bracket a little better. Okay, I'm trying to make it not go out of the page. And then remember, double arrow for resonance, and we're going to do that same thing twice, but now on different spots. Okay, draw it here too. Remember, don't forget your brackets. And our last one. Three, four, five, 6. 2, 3, 4, 5, 6. Don't forget our brackets and the charge. Alright, and that is your resonance structures. And to answer the question, is it resonant? Yes, it is resonant. And that's it.